Afternoon. Welcome back again. I will continue with our discussion of probability theory, and this time I'm going to bring in a topic called conditional probability. In a couple of minutes, we'll be looking at examples which are directly taken from probability theory, and these are all banked on what we call conditional probability, a very important concept in the theory of probability. If you look at my screen here, I have the union defined as I've defined here. The union is basically probability of A union B turns out to be any object or any outcome that falls either in A or in B is also in A and in this case union B. And therefore, if you look at the colored dimensions here, you look at the blue and the yellow. Everything that is either in blue or in yellow, or of course in both, they all turn out to be having the property that they belong to A union B. This is like 1. And you already know about the intersection, which is the green area right in the middle. That's the intersection part. And as I told you, the formula here is the probability of A union B, which is like finding an outcome either in A or in B. That turns out to be PA plus PB minus PA intersection AB. This we have seen before. Let's move into an example now. And the example goes as follows. Again, I've got kids writing tests and I've given them a test and I've counted how many got A and how many got less than A. And also I've kept track of how many were male and how many were females, how many girls were there and how many boys were there. The questions that are being raised again is what we had before, which is like, what is the probability that a randomly picked student is going to be male, or a randomly picked student is going to be scoring A, he would have scored A, he or she would have scored A, and what is the probability that the person I picked is male and he scored A. What is that probability? This and immediately tells us this is a matter of intersection. Now, so far there is not much of a problem. I can probably find that out. But in addition, I'm given another question which says, what is the probability that the person has scored A if he is a boy, if he is male? That means given M, given that the person is male, what is the probability that he would have scored A? This would require me to define some additional theory, and let's see how we move into that. We define what we call the conditional probability. And what we say is probability A given B, probability that the event A is happening given that B has happened before it. This is the probability of A occurring given that B has occurred. And this is given by this formula here, probability A given B, and it's always marked with this slash that you there. You see the slash there? It is equal to probability A intersection B divided by PB. And let me give you a pictorial idea. Let me give you a little idea of how this is done. How did I end up with this thing? I have what you see. I have the set A or the event A, and I have what we call the set B, which is the other event. I'm going to give it a different color. This is set B. A intersection B is this part. That's going to be A intersection B is going to be this part. A intersection B. Now, if I have to figure out the probability of what I said conditional probability, and that I'm going to write as probability A given B, let's look at the total possibilities. Given B means all of B would have occurred, so I divide that in the bottom. So I just call it PB in the bottom. That's the denominator. In the numerator, I only have to carry that part which is common between A and B. That is this part. That is this part. This is the part that would have occurred if B had occurred. Now A is occurring and also B is occurring. This is the intersection part. So what have I got here? What have I got to write here? I have to write here probability of A given B is going to be probability A intersection B, which is this part really. This is the part that is A intersection B, divided by this whole probability. So it's now a ratio of this little thing here divided by this whole thing there. That is going to be my conditional probability. I'm not interested in this part because there B is not occurring. I'm interested in only those parts where B is occurring. B is occurring all over this place, and this is the fraction of times when A and B occur together. So the probability of A occurring when B has occurred all over the place, and the probability of A has occurred in this area. So it's going to be this ratio that actually gives me the conditional probability of A given B. That's this. This is a very, very important formula. This you'll be using many, many times. When you get into probability calculations, you'll be doing this many, many times. Let's see how we use them. What we have to remember, of course, is again a little reminder of what we had done before. We have what we call independent events. And independent events are ones that occur independent of, regardless of what might have occurred somewhere else. So, for example, a Kharagpur IIT student had his bicycle stolen. And by chance on July 15th, it rained in Mumbai. These events really have nothing to do with each other. They are independent of each other. That's like an example of events being independent. And look at this side. I've got, fire in the lab. In the chemistry lab, there was a fire. And, Obama got elected a couple of 100 days back. Obama got elected in the US. Probably these have nothing to do with each other. They are probably independent of each other. And there was a car accident at the gate. At the Puran gate of IIT Kharagpur, there was a car accident. Again, this has nothing to do with Obama, nor did it have anything to do with the lab accident. These are examples of independent events. So I see here independent events thrown together. That's all. On this other side, I've got mutually exclusive events. What are those? I'm tossing a coin and I get, with a certain probability, I get heads. Certain number of times I get heads, and at other times I get tails. And only because these are the only two outcomes possible, head and tail, this sum of the probability of there being a head and there being a tail is going to be 1. Probability of head plus probability of tail is going to be 1. And this is really, if head occurs, tail will not occur. If tail occurs, head will not occur. Therefore, these are mutually exclusive events. So I hope you are clear now about independent events which occur individually regardless of what might be happening somewhere else. And mutually exclusive events are such, if one of them occurs, the other will not. The ones that are mutually exclusive, they preclude the occurrence of the other one. We have to remember this when we are combining events, we are combining probabilities. So events A and B are independent if and only if I do this conditional probability and I find it is unchanged from the probability of A. So whether B had occurred or B had not occurred, it would not really matter for the probability of occurrence of A. If this is the situation, I say A and B are independent. And of course, this would also imply that probability B given A would be equal to PB. Probability B given A would be equal to PB. And now we can go back to the two-way table that we did, and we would like to take a look at what exactly is the situation. So I bring up the two-way table and I have some numbers there, and what I have done is, are the grades independent? And before that, I would like to do a calculation. I would like to go back to that thing there, and I have this problem set which is given to me, and the questions that are being asked in this case: what is the probability that the student is male? What is the probability that he or she scored A? This is randomly picked student. What is the probability that the randomly picked student scored A and is a boy? And what is the probability that if he was a boy, he scored A? This is the conditional probability. Probability of A given B. B has occurred, and now I want to see, B is given to me, and I want to see the probability of A being there. Let's see how we calculate these things. I have the solution here on this little piece of paper here, and let's start by looking at this two-way table. We start by taking a look at this two-way table. What the two-way table does, it allows me from counting, it allows me to calculate the different probabilities in a very simple way, which is just by counting. So here I am using counting, I am doing really objective evaluation, I am not going by opinion, I am going here by hard data. What is the probability of the randomly picked student is a male? Let's take a look at that. How did I get 0.375? The chance of his being male is, those who got A, they were 30, and those who didn't get A, they were 45, so the total is 75. I divide 75 by 200 and I use my machine, and it turns out that the machine gives me a number 0.375. Thus the probability of a randomly picked student being male. What is the probability that the randomly picked student has scored A? A could have occurred two ways. Either he was male or he was female, or the student was female. Therefore, 90 is the probability of any student of any sex scoring A. Therefore, 90 divided by 200. That is the probability that the randomly picked student is going to be scoring, would have received A. Let's try to do that. So what I do is I take 90 and I divide that by 200 and I look at the number, it turns out to be 0.45, and indeed 0.45 turns out to be the answer. See the 0.45 written there. Now let's take a look at the third possibility, probability of A and M. What is A and M? A is, he scored A, the person scored A and the person was male. That is going to be now 30 divided by 200, again by counting, and 30 divided by 200, it turns out, I don't need the machine now, it turns out to be 0.15. That's the probability that the randomly picked student was male and also had scored A. Now this condition, probability of A given M, he scored A given that he was a boy. How do I do that? I bring up my probability calculations and I go to my conditional probability formula, and the conditional probability formula is given as this: A intersection B divided by B. And let's take a look at this. These are all joint probabilities. These are all going to be joint occurrences of things. Therefore, if I have to find the joint occurrence A and M is which cell? A and M is this cell. This is the cell that gives me the count of scoring A and also being male. So it turns out 30 divided by 200, that's the probability of A and M. A and M. That's 0.15. And then the probability of the person was, because when I'm using my formula, when I'm using my conditional probability formula, I have probability A given B, that is equal to probability AB divided by probability B, which turns out to be probability A intersection M divided by PM. PM in this case, I have already calculated, is 0.375. So 0.15 divided by 0.375. This is a very complicated question. Let's try to work it out. 0.15 divided by 0.375 equal to 0.4. So that's the answer. That's the answer right there. So I've solved this problem now, and I've also solved a question that involved conditional probability. Let's go now to the next question. What is the next question? Let's try to get the question now. The question is this: are genders and grades independent? What is the test for independence? Remember now? Recall? Test of independence is PA given B is the same as PA, or PB given A is independent of A, which is it's equal to PB. So let's see if we could work those things out. What I'm going to do is I'm going to work out those probabilities, and if that is so, it also turns out there is a simple test for probability, for the independence of probabilities, and that I'm going to show you just by flipping around a little bit. And I'm going to bring that sheet there. The sheet is here now. Are genders and grades independent? And it turns out then, remember now the intersection. Remember the formula I had. Let me remind you of that formula. Let me remind you of that formula here. Remember the conditional probability formula, which is this. And this formula I could also rewrite. Let me rewrite that for you on a sheet of paper. Then I think it will become a little more clear. The conditional probability formula says P A given B is equal to P A intersection B divided by PB. This I can also write as P A intersection A given B multiplied by PB is equal to P A intersection B, which I can also write loosely as P AB. No problem so far. Now, if A and B are independent, then this guy turns out to be PA and multiplied by PB. This is equal to PAB. This is the result. This is the result I want to utilize. I look at PAB. Is that equal to PA times PB? And this should be true for all outcomes, by the way. You can't just check this in a special case and say that I've got A and B declared to be independent. They are ready to be declared independent. You can't do that. You have to check out all the outputs, all the outcomes. And from that, you should make a general statement. I've verified that in no situation this condition is violated. Then, of course, A and B are independent. Let's see how we utilize that. We go back to the problem. Are grades independent of gender? And I have the solution here. What do I have to check now? I only have to check this condition. PAM. A is scoring A, M is male. So I've got sex here and I've got score here. Is that equal to this? This is what I'd like to check. So really this is being posed as a question. This is being posed as a question. I have already calculated P, A and M in the previous question. I have already calculated P, A and M, and I have also calculated PA, and I've also calculated PM. So I've got all the things. I've got this guy calculated separately, this calculated separately, this calculated separately. I just have to check, is the left hand side equal to the right hand side? That's what I have to check. And what I did was, I took the value of PA and I took the value of PM, multiplied them, and let me just do it for you so that you'll believe that I've done the job. I have 0.45 multiplied by 0.375 equal to, and I get 0.16875. But my God, we should have got 0.15 because that is PM. So it turns out this number is not the same as this. Therefore, what is happening here? This condition is being violated. What does it mean? Grades and gender are not independent. So it depends whether you're a boy or a girl, how you're going to be doing in the exam. That's like this little test here is suggesting that. So it's a question of probability, but we've done this. You already know about this condition here, which is like sum of all the probabilities, they should be equal to 1. If you talk about mutually exclusive events, and it is sort of like this, you go and pick a couple of hats, and there are a certain number of red hats and a certain number of green hats, a certain number of black hats. What is the chance that you'll be picking up a green or a red or a black? They are now mutually exclusive. It will all depend on the fraction of red being there, or the fraction of black being there, or fraction of green hats being there in that basket where all these hats are put there. And in fact, it turns out whenever you've got mutually exclusive events, the union will turn out to be the sum of the probabilities of these two. So this is again a very useful formula which is utilized, and we'll be also using them as we go into problem solving. Now I have a situation here, and I'd just like you to read this and verify that this is so. I'd like you to just read this and verify that being shot in the office, which is a president being shot in the office, dying of, being killed in the office, and having beard, are these two situations independent of each other? Being shot in the office and having beard. Are these independent of each other? This we can verify by going to history and looking at all the data. And if the data turns out to be something different, then we'll say, indeed, they are independent of each other. Having beard has nothing to do with getting shot in the office. Then, of course, I'll ask you to read this slide and work it out from that. Now, conditional probability, this is something I used already. And I told you that conditional probability is something that is there. And what they've done here, they've tried to use the conditional probability formula. And they've tried to show that PA times PB in this case turns out to be the intersection, and so on and so forth. In fact, it turns out PA and PB, if you multiply them, you'll end up with PA and B. But I'd like you to work it out on your own. So I will not solve that particular problem. Instead, I'll be solving some other problem. Let's take a look at the other problem that I'd like to solve for you. I have this notion of joint probability. What is joint probability? It is basically saying, if I have two events A and B, the probability that they will occur together, they'll be observed to occur together. They might not be causing each other, no. All they are saying is, they are observed to occur together. It rains and I have poor marks in the test. It's just joint occurrence, nothing more than that. It's not that one is causing the other. That will require a lot of verification. That will require a designed experiment to really, sprinkle water and see if grades get affected and that kind of thing. Or observe the situation when it is really a cause and effect type of relationship. If that can be verified, then only I'll say A is causing B. Otherwise, they're just observed to occur together. That's all. So it turns out that whenever we talk about joint probability, events are just seen to occur together, nothing more. What kind of events are we talking about? We've got two events here that we are playing with. One is HH, two tosses, and both are heads. That is the first event. First event is, I toss the coin twice and I get two heads. The second event is, I get one head, but first I get a head, then I get a tail. That's one outcome. And the second outcome is, I get a tail and then I get a head. So there are two outcomes now that constitute the event A, event B. It is head and tail, head and then tail, or tail and then head. What is the joint probability between A and B? Can you really work out the joint probability? Can you really work out the joint probability? There's one easy way to do this. And that's what I've tried to do here. What I've done is I've sketched here event A and I've sketched here event B. Notice something. The outcomes have nothing in common. The outcomes are really the sequence of two events. One is the observation of head, then the observation of tail. So if I find head, I say event A has occurred. If I find head and then tail, or tail and then head, I say event B has occurred. Nothing is common between them. If you work out the probability, there will be nothing common between them, and if you go back to that probability of A and B, A intersection B, it will turn out to be the product of PA and PB. You work it out in details and do that. I'm just saying right now there is nothing common between them. Therefore, there being nothing in that intersection, that probability is going to be 0. So in fact, I show it here by saying the set A intersection B is null. The probability of that is 0. If this occurs, the other will not occur. It turns out if this occurs, there is nothing from here that has also occurred there. So the probability that A has occurred, it might be some quantity there. This probability is going to be 0 in those experiments. Let's carry on here and let's go to another example. And I'm going to be showing another example which sort of goes like this. Remember, whenever I said A and B are independent, my test was PA intersection B is going to be PA multiplied by PB. And of course, I give you the reminder that independence does not mean that A and B cannot be observed to occur together. They might be occurring together, but it does not mean they are independent of each other. Independence does not mean they cannot occur together. They might be occurring together, and that's the joint probability. That's the joint occurrence of the two. So there can be an accident, and also there may be somebody scoring C in an exam. Those two events, they may occur together, may not occur together. Sometimes they occur together, sometimes they occur independent of each other, not really related to each other in any way at all. If I have a set of events, if I've got A1, A2, A3, A4, a set of events, then if I look at their intersection, if they are independent of each other, then this relationship will hold good. Probability of A1, intersection A2, intersection A3, and so on and so forth. This is now whatever is common between A1, A2, A3, A4, A5, and so on. That turns out to be the probability of that turns out to be the product of the probability of all the events occurring together. That turns out to be this way. Here's an example. There are two events. The birth of a daughter and the birth of a daughter, birth of anyone, any child with AB plus blood type. Now, AB plus blood type is determined by biological considerations, and different biological conditions lead to the birth of a daughter. These two actually turn out to be independent events. Again, if you do this test, PAB, it will turn out to be PA times PB, and that is the test for independence. Or you could actually say, in another way, you could really say, if I had to test this, I'll say P A given B. This turns out to be PA. On the right hand side, I do not have B influencing anything at all. And the same thing will be applying. If A and B are independent, I could say P B given A, B given A. This will turn out to be equal to PB. That's all. These are tests of independence. These are tests of independence. They actually say that B really has no influence on the occurrence of A, or A also has no influence on the occurrence of B. And let's try to work out one example. Let's try to work out this example. We are working out many examples, and obviously you can stop the tape and you can actually rewind and so on. You could do that, but let's take a look at this example here. I have the joint occurrence defined here. How have I defined it? I've defined it like this. A drug is used to treat people, and these people could be men or women. And the result of this administering this drug is either the drug is successful, it heals people, or it fails to heal people. And some data has been collected. So the drug was given to women and also to men who were sick, and in a certain number of times the drug was found to heal people, and in certain other cases they were found not to heal people, and the fractions are given here, the ratios are given here. So I have here a total of 200 plus 1800, that's 2000, and 1800 plus 200, that's again 2000 again. So 4000 people were given this drug. 200 women, they got cured. 1800 men got cured. 1800 women could not be cured, and 200 men could not be cured. And let's talk about the events that we are going to be testing against each other. A is the event that the patient is a woman. What is the chance of the patient being a woman? It is going to be if the count comes in this column. This is a chance which is like 50% chance of the woman, of the randomly picked patient being woman. And the chance of the drug failing, I go to the failure row and I find 1800 plus 200, that's again 2000. So what I have here, I've basically got a count of how many women were there in the test, and also how many times the drug failed. That count also I have. the question I'm asking is, are A and B independent? What are A and B? A is the event that the patient is a woman, and B is the event that the drug failed. Are they independent of each other? Are these independent of each other? Let's try to see how we do that, how we work it out. And for that, what I've done again is I've taken a print of the slide and I've worked out the examples for you. I have here, first of all, you'll notice I've done the totaling. So I found out how many women were there in the test, and that turns out to be 2000. 200 plus 1800 is 2000. How many men were there? That again is 2000. How many successes I had? I had 2000 successes, and I had also 2000 failures. A total of 400 people, 4000 people were involved in this. Now let's take a look at this quantity here, which is like the product of, which is the joint probability of women and the drug failing. And that I can find by going to this joint probability table here, and it turns out if I have to look for that count, that is shown here. This is the count of the patient being woman and also the drug failing, that is 1800. So 1800 divided by 4000, which is the total number, that turns out to be 0.45. That is the probability that I had women tested and the drug failed. That is this probability. This is women and failure. That is this probability here. What I then do is I go into the pieces, the parts of it. I look at the probability of failure, and this is really called the marginal probability. The marginal probability of failure, that turns out to be some number. That will be like probability of failure is 2000 divided by 4000. That is this number. And the other part is the patient is woman, and that again turns out to be, if I go to this column and look at the total, 2000 divided by 4000, that's this column here. So I've got 1 by 2 divided by 1 by 2, that's 1 by 4. And look at WF. WF is the joint probability, which is 0.45. It is not equal to 0.25. Therefore, it turns out these are not independent. These are not independent. So the conclusion is that the test is, the situation here is not independent. The drug failing and the patient being woman, these are not independent events. This I get by just applying this little formula here. This formula is the probability, is the test for independence. This is really the test for independence. This is the test for independence. This is the test. That is the test for independence. That's what I've done. Let's see what else we are being told about independence. And I'm going to be coming back again to one of the examples. Consider the example when I toss the coin twice. And the outcomes for event A was defined as head and then tail, or two heads. And B was the event head and tail. Will the event A be independent of B? This is the question I have. I have this question. What is the test I'll be applying here? Again, PAB, is it equal to PA times PB? And for that, what I have to do is I have to calculate PA, and also I'll have to calculate PB. And I've done that, and let me show you what the calculations look like. It turns out PA, which is like head then tail, which is half times half, that turns out to be 1 by 4. And also I could have the same event occur if I had two heads, and the chance of them occurring like this is again 1 by 4. So 1 by 4 plus 1 by 4, because these are two different outcomes. And I'm talking about this occurring or this occurring, therefore I add the probabilities. So PA has the probability of 1 by half, 1 by 2. PB is now this case here, first getting a head, then getting a tail. Getting a head is 1 half, and getting a tail is also 1 half. When I multiply the two, because they must be together, that turns out to be 1 by 4. Now I've got PA and PB. what is the chance of my PAB? PAB is what? PAB, that is when A has occurred and also B has occurred. It's a very funny situation. I have situation like this. I have A here, and A consists of two things. A consists of HH and HT. And guess what B consists of? B consists of this part. This is B. So what is going to be the intersection of A and B? That is PAB. A intersection B. What is that set? That is this. And what is the probability for this? That is 1 by 4. So here again I've got a situation when PA times PB does not equal this. Does not equal this. That means again they are not independent of each other. And you can work out the other examples. On your own you can work out, and I'm providing you the solution, and you can come back and check this again. Check to make sure that yes, indeed there is a problem there. That is something we could do. Let's take a look at another situation when I'm talking about conditioning. And let's see how we work with the conditioning problem. I start by again having a joint table, and the joint table looks like this. If you look at the screen here, the joint table looks like this. And what I'm going to be checking is what is going to be PB given A. I just have to calculate that, and for that I'll be using the joint table, and I'll be looking up for PAB. I'll be looking out for PA, and I'll work out this definition now. This PB given A will be equal to PBA divided by PA. That's all. PA given B will be equal to PAB divided by PB. And that's exactly what I've done. If you just see that situation there, this is exactly what I've done here. So conditioning calculations are quite easy and quite straightforward. And what have I done here? I have here, if you look at my sheet now, I have here PB given A is equal to PAB divided by PA. That is PB given A. And I got this PAB already calculated. I did the fractions before, and so I know that those numbers there, I've got 0.45 divided by 0.5, that is PA. That turns out to be 0.9. That's one conditional probability. The other conditional probability turns out to be PA given B. There is some symmetry in the data. Therefore, that answer also turns out to be 0.9. Now let's just go back and remind you how I found my PA and PB and so on. What is PA? PA in this case is going to be patient is woman. Patient is woman, that really means I have to count up the number of women. That's 2000 divided by 4000. That's going to be my patient being woman, which is this part. That turns out to be half. There's a 50% probability, because half the population is women. This 50% probability that a randomly picked person, randomly picked patient is woman, and that turns out to be half. What about PAB? PAB is when the drug fails when a woman is using it. And that is this cell here. This is the cell where I've got women using the drug and the drug failing. So that 1800 number I put there. And I have 1800 divided by 4000. And that turns out to be, as we've done before with our machine, it turns out to be 0.45. This is how I found PAB, which I bring here, and I divide that by PB, and I end up with my other numbers here. So conditioning probabilities are quite easy to calculate once you have the discipline there. With this we can move on, and we can actually test if there is any relationship there. If given that A is independent of B, what is the relationship between PA and PB? This I'm sure you can work out. Let me ask you the question again, and I think you'll understand that. There are two events. One event is A, the other event is B. And what they are saying is A is independent of B. That means PA is the same as PA given B. This is what they are saying. They are actually saying that. What is the relationship between PA given B and PA? It turns out they are equal, because this is not dependent on B, this is actually equal to PA. If I only know this, I don't have to worry about this, because A in no way is dependent on this. So this conditioning really has no effect at all. Whether B has occurred or not, it has no impact on the occurrence of A. So it's a fairly straightforward question, nothing more. Just a little tricky question. They just slipped in this little question for you. Then we move into something which is an application of what we've done, and this turns out to be a very vital sort of application of conditional probability. And let me tell you that it also gives us an indication of how good our quality control factor, quality control instrument should be like. And I'll illustrate that using some assumptions, and I'm going to solve it for you. I'm going to show you the solution also for this. Let me first give you a picture. Let me first give you this scenario. And to do that, what I'll be doing is I'll be bringing you a situation in a hospital. The hospital is using some device, maybe mammogram or something it is using, to test, or some sort of a scanning to test to see if a person has cancer. It turns out that if the test says positive, it's not true that the person always has cancer. In fact, if the person does have cancer, look at the screen now. Look at the screen now. Look at the display here. It says if the person has cancer, the test will be positive. The probability of that is only 0.92. Only in 92% cases with a real cancer, the test will say that the patient has cancer. Really, the patient already has cancer, but there is only a 92% chance that the test will catch it. The reverse situation, I bring it a healthy person, and he goes there, takes the test, does his mammogram, and then the test shows positive 4% of the time. So it's a perfectly healthy person. He takes a test, and because the instrument is not perfect, 4% of the time it gives you a faulty result. Now these numbers, 92% seems sufficiently high, and 4% seems sufficiently low. So you might say it is okay. I think I'll get that instrument. I'll have it installed in our hospital. Now, what we'd like to do is we'd like to do this analysis using probability theory. We'd like to find out, is it reasonable for me to purchase this equipment? How often is it going to give me false signals? And what kind of false signals? We'll work that out. We'll work that out. If a person is randomly selected and his test is positive, what is the chance that he really has cancer? Think of this again. Let me repeat the question. The test is positive. What is the chance that the person really has cancer? Knowing that the instrument is not perfect. Let's try to work this out. What we've been given, of course, is that in general, in the wide population, 0.1% people have cancer, which is probably true for this area of the geography. It would be quite different if you're in New Jersey or some other place where the chance of having cancer is, it could be double digits, because there are a lot of chemicals in the area, a lot of garbage dumps and so on, and the air is not clean and so on and so forth. It would be true in many other places also, but New Jersey I know in particular because I lived there and I saw all these problems there. Let's see how we work this out. So what is the data that has been given to us? I'm first presenting you just the data, and the data is this. In the wide population, 0.1% of people have cancer, and that means 0.999 is the probability of the person being healthy. No problem there. And the instrument's capability is the following. It shows the test to be positive when there is cancer 92% of the time, which some people may think is pretty good. And also, unfortunately, for a healthy person also it says that the person has cancer 4% of the time. This is the instrument's performance. The question that is being asked, this is a managerial question. Will you rely on this test equipment? And will you start a treatment only because you start a cancer treatment which is pretty severe just because the machine said you have cancer? Will you do that? Given this being the record, this being the story. Let's see how we solve this problem. What I'll be doing is, I'll be walking you through some calculations. Be just a little patient, and I'm going to work out the problem for you. And we'll be concentrating straight on the sheet that I've worked out for you. It took me a little while, but it still could be done on one sheet. So I thought I should preserve this for the class here. These are given. These things are given to us. The probability that the test is positive, given that there is cancer, is 92. The probability that the test is positive, given that there is no cancer, that's a healthy body, is 4%. In the wide population outside, the probability of a person having cancer, is only 0.001. And the person being healthy, that means no cancer, is 0.999. These are given to us. Now let's try to work out some questions. What is the question that I'm asking? I'm asking this question. What is the chance that the person has cancer given that the test is positive? Given that the test is positive, what is the chance that the person has cancer? This is what I have to evaluate. This is what I have to evaluate. And for that, actually, I will have to go back into what we have here, the data. I'll have to find this, I'll have to find this, and I'll have to find this. How did I find this formula? This came straight from our conditional probability formula. And I'm going to show you that formula in just 1 minute. I'll show you. In fact, what now we have to do is, we have to look at these things. Look at this intersection here. Probability that the test is positive and the person has cancer, it is equal to the probability test is positive given he has cancer multiplied by the probability he has cancer. Do I have this data? Yes, I have this data. So I have this data here. Do I have this data? Yes, I have this data. It's also given to me. So I can calculate this quantity. This quantity I can calculate without any trouble. And it turns out this is also equal to the probability this way, because I can flip these two. This is a intersection condition. So whether I take C first or I take plus first, the positive indication first, it does not really matter. So here what I've done, I've made C conditional on the test being positive and this. So I have actually on this side, I have something that is equal to this. On the left hand side, I've got the quantity. So I've got a quantity, I've got this quantity, I know its value. Its value is going to be the product of these two. That I can find from these two. Then I look at this quantity here, which is the probability that the test is indicated to be positive. When can that happen? That can happen by this. Probability that the test is positive given that the person has cancer multiplied by the probability that the person has cancer. And that is found from here, so I know this and I know this. No real problem there. And then this part, which is like probability that the test is positive given that there is no cancer multiplied by probability that there is no cancer. Where can I find this? I can again look up my given data, and it turns out that this I know and also this I know from here. So I know all quantities. So I can evaluate this quantity for sure. Now the only thing I need to find out is probability of C given that the test is positive? Because this is something that I'm going to be finding out. I'm going to be calculating that. So let's try to see if I could calculate this quantity here. What is this now? What is this probability? This is the critical question. What is the chance that the person has cancer given that the test is positive? Now look at this statement here. Look at this statement 1. Statement 1 says probability that test is positive given that the person has cancer multiplied by this. This is the same as probability of test being positive and probability having and the patient having cancer, person having cancer. That is also equal to, this is like probability A given B multiplied by PB, and this probability B given A multiplied by PA. That's what it is. So I've really written this same formula once here, another time here, just by changing the order of the things. So it's the same formula. This is valid from the probability of conditional probability formula. I use this formula and I'm after this quantity. What is that quantity? Let's try to put a green bar there. I'm after this quantity. This is the quantity I'm after. I know this and I know this. And this quantity I've already evaluated by equation 2. So I know this and I know this and I know this. Therefore, I can find this. And this I write right here. Probability of there being cancer given that the test is positive is equal to this quantity here. I just took this. This is what I took and I put that in the numerator and I divided by the denominator there. So from 1 I found this. Then from 2 I find the probability of the test being positive, which turns out to be this quantity, this quantity. This is the quantity that I put down here. Using which equation? Equation 2. So I have a quantity here where I've got all the numbers. I've got 0.92, I've got 0.001, I've got 0.92 again, I've got 0.001, and I've got 0.04 given to us, and I've got 0.999. This I've done. And if I do that, and I use my machine, I do tuck, 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 whatever, and so on and so forth, and I do some multiplication, divide, and so on, I get 0.0225. That is the probability, believe me. That is the probability of a person having cancer if the test is shown as positive. The instrument says the person has cancer and is truly having cancer is this. So the probability truly having cancer given that the test is positive is only 2%. Will you trust a machine like this? Will you trust a machine like this? What we have worked out is not known to many people in medical practice because they have not gone through this. And just see how serious this matter is. How can we fix this situation? One way is start playing with these numbers here, this 0.92. Notice here there is a quantity called 0.92, which is the goodness of the instrument. This is also the goodness of the instrument. These are the factors. I need not really worry about population statistics, but I must worry about this number and this number. These have to be sufficiently high. These have to be high. In fact, this has to be low and this has to be high. This has to be low because this is saying there is cancer when there is no cancer. And this is saying there is cancer and it's saying positive. This should be as high as possible. What we have done, we have taken this to 0.999 and we have reduced this to 0.001. If you do that, this result is still only 50% okay. That means you need a machine that must be much better than what these fellows are supplying to you. The performance level at which these people are supplying it to you. This is something we got to keep in mind. And this is the analysis that you got to go through. This is the analysis you got to go through before you make a purchase. You should not go just by this 0.92 and 0.04. They look great. They sound very good. But when you actually do the calculation, what is the chance of the person really having cancer when the test is positive? That turns out to be really small, 2% only. And obviously, we cannot really send these people for chemotherapy. With this sort of probability, we cannot send people who indicate to be positive to chemotherapy. We just can't do that. We cannot do that. This just kind of gives you an idea how important this conditional probability theory is. It's very, very important. This gets into quality assurance, this gets into production manufacturing, this gets into any kind of improvement that you're looking for. Like, for example, if you want to remove false alarms or bad treatments, a hospital is a test facility. A hospital also is a service facility. It should provide good service. If it is based on this sort of data, it's not really possible for this particular facility to survive for too long. And people can take them to the court. If this is the kind of instrument that is being used and false treatments are being given, only there is a 2% chance of the person really having cancer when the machine says he has cancer. That being so low, people can be taken to court. And just be mindful of this. So when you get into a situation like this, please think of this example. And this is a pretty famous example. It's used by many different people. So will you really get a treatment? And our answer is going to be plain and simple, no. If this is the performance, if this kind of performance is what you are getting from the instrument, you should not get treated in that hospital. Certainly you should not go for treatment. Rather, you should try to get other tests and try to see if this number could be improved. And even at 0.999, it's not so good. So that's like a lesson for us. We'll continue with this as we move along. Thank you very much. Thank you.